1 second. Hold up how many substitutions you found just right away. I'm seeing a lot of 2s. Good. Yeah, there's a trig identity for the numerator and the denominator. And this is the substitution that you should have gotten. Cosine squared over cotangent squared. Once you do that, rewrite that cotangent in terms of sine and cosine, and then keep change, flip it. That is the answer. Good job. Getting the hang of it? Yeah. Just takes practice. And Miss Bryant told us we were covering this next time. Took like probably an hour and worked through all the problems because I needed to refresh it myself. Feeling good? What, did you get that?
Yeah. I actually keep changing flipping.
Yeah, but you when you keep change flipping, you make it. Yeah, exactly. Yeah, exactly. Well, just read flip.
Oh,
That's why right from every step, it'll be harder to make a mistake when you're super, super detailed. We keep it cosine squared over 1, change, we change it to multiplication, flip. We know cotangent is, I'm just going to write C and S, cosine over sine. So cotangent squared is cosine squared over sine squared. So if we flip it, it's going to be sine squared over cosine squared. And then when we multiply fractions, what do we need? Nothing. All we need when we multiply fractions is for it to be 2 fractions. After that, it's just 2 individual multiplication problems. So we would have cosine times sine over cosine. What's going to cancel? Yeah, there's a cosine upstairs and downstairs. They're going to cancel each other out. So then it's just going to be sine squared over 1. So I'm not even going to write it as a fraction. Our final answer would just be sine squared x. If you're not sure when you're done with a simplified problem, don't freak out. That's normal. But stay with me. If we have only 1 trig function left or 2 base trig functions multiplying together and they're both in the numerator, you can feel confident that you're done. So right now we have, well, it's to the squared, but we have 1 trig function in the numerator. There is nothing else we can do to make that more simple. So we are good. We have ran our gas tank out. If it was like 1 over sine, we wouldn't be done because we'd have to bring it upstairs. But once everything's upstairs and there's no identities you can do, you are done with your simplification. Usually when we're simplifying, we want to get rid of any addition or subtraction signs. Here we got rid of them when we plugged in the identities. Normally, they'll kind of get rid of themselves. But that's just kind of a nice little rule of thumb. Alrighty, so we're going to kind of quickly go through some of these problems. So right when I show a new problem, just write it down in your notebooks as fast as you can so then we can go over them. It's going to kind of be a rapid fire session today because I want to leave time for homework. So just make sure you're staying with me. And you can write that this is a simplify. No, this is a verify question. I'm sorry. This is a verify question. Verify. Usually when there's an equal sign, we're verifying. If there's not an equal sign, we're simplifying. Give me a thumbs up once you have the problem right now. Yeah, most everybody? Good. All right, so when we're verifying, the first step is to see if any identities hit us in the face. There's a lot of squareds happening, and there's subtraction. When we know there's squareds, like something squared, and there's addition or subtraction, we definitely have to look we have to like take a second look at the problem. So here there's secant squared minus sine squared times secant squared. We got to take a closer look. Now right off the bat, there is an identity we can apply, but there is something else. Who thinks they know what we can do to simplify that left-hand side? What do we do with secant squared? Very close. But I think there's something we can do even before that. GCF. Yes, this is a GCF problem. Whenever you see a GCF, whenever there's addition or subtraction, and there's something multiplying in both terms, you should pull it out. That is like a red flag for us that we kind of just need to know GCF, pull it out. So if we pull out our GCF here, which is sine squared, or secant squared, I'm sorry. Good morning. Secant squared, which is our GCF. Remember, left in the parentheses is still going to be a subtraction problem. Yep, we divide each term by the GCF. Secant squared divided by secant squared is going to be 1. We keep the subtraction sign. Sine squared, secant squared divided by secant squared is just going to be sine squared. So now we got this. Every step, every new line that we start, we need to check for trig identities. What's the trig identity that we see here? Yeah, 1 minus sine squared. What's 1 minus sine squared? Cosine squared. You have to be able to identify that. You have to be able to. As you do more and more of these problems, hopefully you're using the pink sheet less and less because you're just getting more comfortable with those equations that you have to memorize. If I were you guys, I would memorize those top 3 Pythagorean identities. I would memorize them. I would write them at the top of my test, right off the bat. From there, every time you have something that looks like it could be a Pythagorean identity, see if you can rearrange one of those 3 equations to make it exactly equal. If you do that, then you don't have to memorize all 7. You just have to memorize the top 3. Because remember, the bottom 4 are just rearrangements of those top 3. So anyways, I got caught on a tangent, but we have secant squared theta and then multiplied by cosine squared theta. Who remembers the hard and fast rule we have when sisters are multiplying by each other? They equal 1. That is something that you can just do on a test. If you wanted to write it out as 1 over cosine squared theta times cosine squared theta and cancel them out, that is perfectly good. That is perfect. But if you wanted to just jump from sisters multiplying by each other to say they equal 1, that all of that is going to equal 1, that works too. All of the sister rules apply when there's an exponent as long as the exponents are the same. If we had secant squared times just normal cosine, it wouldn't apply. But since these exponents are the same, our normal sister rules apply. A sister times a sister, so secant times cosine, cosecant times sine, cotangent times tangent. They're going to cancel each other out to 1. So now we have 1 equals 1, and we are good. We have verified that equation. Any questions on this problem? Pretty straightforward. So I'm going to keep rolling. Write this down. It should be quick. This is a simplify question. We'll always tell you verify or simplify, but one way you can know is if there's not an equal sign, you are simplifying. Yes. I'm also recording this, so if you want to go through the work again, just watch the recording. It'll get posted during 4. But if you want to just look at the work, just look at that. It'll be good. All right, so hopefully you have it copied down by now. It's a simplify question. Simplify. There's a reason I'm not an English teacher. I think I spelled that right. All right, so what do we notice about this fraction right here? They're sisters dividing each other. Now we have a rule for when they multiply each other. Let's see what happens when they divide each other. When they divide each other, well, first things first, I'm going to rewrite them in terms of cosine and sine. So tangent is sine over cosine. And cotangent is cosine over sine. And then we would still have the plus 1. So the way we would simplify a fraction over one fraction, remember we can't keep change flip until it's one fraction over one fraction, as I already said it, keep change flip. You keep the numerator and you multiply by the reciprocal of the denominator. What's going to happen when we multiply across? Are things going to cancel? No, they are not going to cancel because there is nothing the same in the numerator and the denominator. What's going to actually happen is we have sine squared theta over cosine squared theta. Anyone know what that equals? Tangent squared theta, exactly. Remember, the squareds don't change our rules as long as they're to the same power. So sine squared theta over cosine squared theta is going to be tangent squared theta, just like sine over cosine is tangent. So that's going to equal tangent squared theta. So now we have tangent squared theta plus 1. That kind of smells like an identity to me. There's something that's squared and it's an addition or a subtraction sign. So what I would do is I would check my equations. Exactly. We see if we check our equations on our pink sheet, which remember you have to start memorizing. You will not get on your test, but we have seen how vital they are. That tangent squared plus 1 is secant squared. It's a simplified problem. We have everything upstairs. We got rid of any addition or subtraction signs. We can feel confident. There's no more identities to apply. We can feel confident that that is enough work to show. Alrighty, I told you guys it would be a little bit rapid fire. I'm going to move on to this one. It looks nasty, right? But it looks very similar to a nasty one that we had yesterday and went over together. Yes, yeah. Don't feel like you have to use that funky variable. Maybe that's I'm not good with Greek variables. That might be a alpha. Is it? Yeah. Okay. Yeah, it's just a variable. We'll give you x or theta on the test. But yeah, those alphas you can just substitute out and substitute in an x or a theta, whichever you like more. So is this a verify or simplify? We'll always tell you. But yeah, it's a verify. There's an equal sign. So big picture, we see that we have one fraction and we need to turn it into an addition problem. We have one something on the left-hand side and we have something plus something on the right-hand side. I'm sorry that language isn't very technical, but that's how I think about it. We have one something over here, and somehow in our work, that needs to break into something plus something. So why don't we just break this fraction right away? Does anyone remember from yesterday how we can break this fraction up? Yeah, we break it back into two fractions adding each other. Think about it like this. If we only have one denominator and we have an addition problem in the numerator, we pretty much are cleared to do common denominator fraction addition backwards. And now that was a lot of words. If that confused you, I understand it. But this is what it looks like. We can rewrite this as 1 over secant, and I'm going to use x, plus cosecant x over secant x. When you break it over multiplication, you can just pull something from the numerator out of the fraction. When you break a fraction over addition, each term is going to get the denominator. If we went backwards, we would just be doing fraction addition. We are just breaking apart fraction addition. What do we need to add fractions? A common denominator. So if we break apart fractions over addition, they better each get the denominator. Now all of a sudden, this is going to simplify pretty nicely. Remember, we always need to kind of keep the right-hand side in the back of our head. We know that we're trying to get cosine and we're trying to get cotangent. So we need to kind of be looking for cosine and cotangent at every step. Does anyone see a cosine on the left-hand side right now? Yeah, 1 over secant exactly equals cosine. That is a reciprocal that we know. We know when a sister comes upstairs, it turns into its original form. When secant comes upstairs, it's going to turn into cosine. And then this cosecant over cosecant, it's a weird one. It is a weird one. But let's take a second and look. Cosecant over secant is going to be 1 over sine divided by 1 over cosine. We good with that step? Once we do that step, we are good to keep, change, flip. When we keep, change, flip this, so all I'm doing is taking this term. I don't want to rewrite the whole thing. When we keep, change, flip it, we're going to keep 1 over sine. We're going to change it to multiplication. And we're going to flip it to cosine over 1. We see that when we keep, change, flip it, we're going to get cosine over sine. What's cosine over sine? Cotangent. It is cotangent. So once we keep, change, flip it, we can feel confident to write as our next step that this is just cosine x plus cotangent x. And that exactly equals the right-hand side. You can circle that and be done. I would have done that over there. I just wanted to be able to, for you guys to see it and kind of move through it quickly. Whenever you start with a fraction and you end with an addition problem, right off the bat, you should look to see how I can break up that fraction. That's now 2 problems in 2 days where that was kind of the key to saving yourself some grief. From there was that little extra step of knowing cosecant over secant was 1 over sine over 1 over cosine. But if you're able to do that, you're good. And whenever you kind of get stuck, like if you're like, I don't know what to do with cosecant over secant, turn it into sine and cosine. That's always a great thing to fall back on. Great. One more in this kind of rapid fire, simplify and verify section. So get this written down. This is just a simplified problem. It is so important to remember that when you're simplifying, you need to get rid of all of the addition and subtraction signs. I don't know if we've had a single simplify problem where at the end there is an addition or a subtraction sign. Not necessarily that. Verify is when there's an equal sign in the problem. Simplify is when there isn't. But we will always tell you whether we want you to simplify or verify. There's someone at the door. Alrighty, so how do we get rid of an addition sign between two fractions? Well, sorry, bad news, we gotta add them. I know, adding fractions is not my favorite, especially when we aren't given a common denominator. So yeah, this is a stinky one where we have to establish a common denominator. But let's work through this together. When we need a common denominator, what's a surefire way to establish it? Yeah, no, it's weird to say, but we would multiply this first one, top and bottom. Some people were only doing top and bottom by the denominator of the other fraction. So this turns into, let's see if I can write small enough. This one is going to be 1 plus sine over 1 plus sine. And the important thing to remember is that this whole denominator needs to multiply by this whole numerator and this whole denominator. So if you're someone who struggles with the PEMDAS, we've talked about it, surround everything with parentheses. This is what you're doing. You're multiplying this whole thing by this whole thing. This whole denominator by this whole numerator. And it's important because we see these denominators might turn into a little box problem. On the right-hand side, we're going to multiply by the denominator of the left. I shouldn't say right-hand side. On the right fraction, we're going to multiply by the denominator on the left side, which is 1 minus sine and 1 minus sine. If I was being mathematically correct, I'd be writing theta. I just kind of want to save space. And I'm surrounding everything with parentheses to make sure they get grouped correctly. So now let's rewrite this bad boy. When we rewrite it, the denominator, we're just going to have one of them. That's the reason we established the common denominator. So you can pick that one or you can pick that one. It's fine. I would say when you're adding or subtracting fractions, at first, just keep the denominator, like don't multiply it out. Because sometimes one of the factors is just going to multiply out right away. So keep it as 1 plus sine times 1 minus sine. I wouldn't worry about multiplying out that denominator right away. In this numerator, let's see what's going to happen. This numerator is going to be 1 plus sine times 1 plus 1 times 1 minus sine. So the way we would do this, especially if this wasn't a 1, is we would have to distribute. One number times two numbers. Here it's nice that it's a 1, so essentially it's just going to be that plus that. So we have 1 plus sine theta plus 1 minus sine theta. One thing to note, it doesn't apply on this problem, but if you're subtracting fractions, and this got a lot of people in the homework, if you're subtracting fractions, that negative sign, that subtraction sign, needs to distribute to everything you find when you multiply the two numerators together. And that's why parentheses are your friend. Here it's an addition, so we didn't have to really worry about it. So great, now we have it in terms of one fraction. Let's see how this simplifies. When this simplifies, we're going to have 2. And these signs are going to cancel out. Do you agree with me? You combine the like terms, we're going to have 1 plus 1, which equals 2, and sine minus sine, which is 0. So we have 2 plus 0, which is just 2. Now, I don't really know what we can do with 2 over 1 plus sine times 1 minus sine. So on this problem, we're actually going to have to multiply out this denominator. I didn't want to do it right away, but we got to do it now. If we multiply out this denominator, remember, we can't just say that it is 1 times 1 is 1, sine times negative sine is negative sine squared. We cannot just multiply these terms together because there is addition and there is subtraction. This is a box multiplication problem. The way this would box out is you would have a 1 and a positive sign and a 1 and a negative sign. We would have positive 1 and positive sign. We would have negative sign and negative sine squared. So funny enough, this one actually does work out. And the reason it does work out like that is because it's the same terms, and in one there's addition and in one there's subtraction. This is essentially difference of squares from algebra backwards. But if you're not 100% positive on that pattern, box it out, box multiply it out. Because we see that sine minus sine is going to cancel, and we're going to be left with 1 minus sine squared theta. Do we have an identity for 1 minus sine squared theta? Let's talk about it. Our exact identity is cosine squared theta equals 1 minus sine squared theta. Is that exactly what we have? Yes. So we are good to just substitute in a cosine squared theta. On the homework, there was one question where we had, I think, sine squared theta minus 1. Let's think about that. Sine squared theta minus 1, if you pull out a negative sign, we then get 1 minus sine squared theta. So if you have an exact identity, but the signs are flipped, it's a positive sign and a negative 1, that would actually equal negative cosine squared theta. It appeared on one homework question. If your identity is almost exact, but the signs are just flipped, it's a positive sign and a negative 1, that's still an identity, it's just the negative identity. It's really tricky. I don't even know if we would throw one like that on you on a test. I don't make the tests. So yeah, we have 2 on this problem over cosine squared theta. We're not done until everything is upstairs. We bring that cosine theta upstairs, and we get that our final answer is 2 times the sister of cosine, secant. 2 times secant squared theta. If it seemed like today we were going really fast, well, first thing is we were. Oh, sorry, I pressed the wrong button.